Good afternoon. I'm Valdenegro, and I'm here with my colleagues Martinez and Julian Rozo, and today we're presenting our rapid assembly of the global microclass aircraft. The objective for our project was to design and develop a microclass aircraft that could fit in a 6-inch diameter tube that was no longer than 70 inches long. This aircraft was meant to use for the 2017 SAE Aero Competition. Another requirement was that it had to be rapidly assembled and deployed from by hand. The reason why we took up this project is we feel by taking up these competitions, where nationwide competition, we can encourage Florida International University to expand their aerospace studies. We also, an object like this is very important in the military industry and also in the search and rescue industry. And to give a quick review of how our presentation will go, we have to understand our design sequences. So we had a design phase, and then we went to the manufacturing phase. But as while we were manufacturing, we saw that things could change, things could be improved, and things were improved. So we had a first iteration, a final, second iteration, and now until we achieved the final prototype.
So everybody in this room understands that aircraft design is challenging at best ideal case scenario. In our case, with no experience, it was nearly impossible. However, to achieve what you see here today, we follow mainly two books and gather as many different opinions, different resources as we could. And the books are Conceptual Approach by Raymer and Simplified Aircraft Design. So what the book gives you is a kind of a timeline that you can follow. And if you follow each one of those items, you are able to complete your design and produce something that actually performs the way you intended. So to begin the design, we actually had to either look at the constraints that we had originally or make some of our own, because there is no such thing as a carte blanche in engineering. You have to have some constraints in order to have a product. One of the constraints that Vlad mentioned is the size of the container. For ASPED, the competition specs, we have a 6-inch container, and if you have a container that's longer than 70 inches, you start losing points. We made our objective to be at least below 60 inches. That's how we came up with a wingspan, and because of the size of the container, we already have the port. And if you know, basically when you have the wing size, half the pilot is one. And that's one of the advantages about why we were able to compress such a development cycle of a UAV, which is a plane, into only 8 months. So another thing that we had to worry about is the payload fraction. It is a competition, therefore we had to stay competitive. We had to weigh in some pros and cons that we'll mention later. And we want a thrust-to-weight ratio of at least 2 pounds because it's going to be end-launched in any condition whatsoever. You can have tailwind, you can have headwind, and so on. To begin our analysis, we had to look at the regime of flow that we're going to be playing in. Because of the small port of 5.75 inches, the relatively cold temperatures, and the assumed cruise speed in the beginning of around 13 to 20 miles an hour, we use those parameters to calculate Reynolds numbers, which then we input into a very basic CFD program called XFLR5. XFLR5 allowed us to take different airfoils, basically run a comparative analysis to see which one will perform better for our application. These numbers are to be taken with a grain of salt, of course. This is not a professional CFD program, but it gives us a good bench line and allows us to do sizing and to estimate some of the performance characteristics. So this is our first design alternative. Some of you were here for Senior 1 presentation and you remember this one. It is still the most aerodynamically efficient design. However, there is some obvious drawbacks such as stability. As such, we came up with a different design alternative, which added a tail, at which point we started losing some of the performance. However, we figured if we have a tail, what the heck, let's just go and put a conventional wing on it, which is what you see here today. And those are the characteristics we have. We have a ridiculously high lift of 1.97 for an aircraft of this size, and a relatively high drag, and a very low cruise speed. Next slide. We have to weigh in different materials and constructions. On one side we had complexities and simulations, on the other side we had mass manufacturability potential, and on the other side we had basically the ability for us to actually manufacture it. So we had aluminum and carbon fiber on one side, and then wood on the other side. Obviously we chose wood because we wanted to be able to achieve something really quick in the time that we had, and this is what we did. We ran some analysis on ANSYS structural for the most part, and the idea behind it was to optimize the fuselage structure to find the loads. There's no landing gear on this plane, so we're going to be belly landing. there's a propeller running around, which is the result of our belly landing. So our simulations were correct. We over-designed the aircraft on purpose. We took some assumptions as far as the materials go. We didn't include ultracoat in the simulations. However, the ultracoat makes the structure more rigid. We originally predicted a 3 inches deflection at the tips. After adding the ultracoat, the deflection was essentially less. However, a side benefit of this deflection is that our aircraft is more stable because it has a natural dihedral angle. So our factor of safety, we have different components which may force us to have different assumptions about how we were approaching the analysis. So for wood, we were fortunate to find a USDA source of material properties that allowed us to treat wood as a realistic orthotropic material, the way it is. And because of the complexities involving carbon fiber analysis, we had to assume orthotropic, linear orthotropic behavior as well. However, we got relatively high safety, factor of safety numbers. The lowest is 1.75 on the leading edge, which is, again, once you add the ultracoat, it will become way higher than that. So again, because we're belly landing, we had to do some analysis on the fuselage. This allowed us to minimize the structure that we didn't want. We used fillets wherever we could to minimize stress concentrations. Next slide. And because we're using a motor with relatively high cost, we had to run a separate simulation just on the firewall where the motor is connected to. Next slide. And this study is about deflection. Basically, what happened from this is we iterated from the results. The deflections were a little too high for our liking, so we had to add some additional bulkheads, which make the structure a little more rigid. You cannot actually see it here, but if you open the aircraft up, you can see that there's 2 more bulkheads added because of the simulation result.
So for the manufacturing process, as Vlad mentioned, it was very important to make our project as streamlined as possible, meaning that we were trying to reduce the aircraft's weight as much as we could. And using different manufacturing techniques that we learned through the Aerospace Engineering Club, we were applying those. Slide, please. So here we have the airflow S1223. We went to 3 different iteration processes. Our first iteration process was just a basic airflow where no cutouts. So it kind of made our wing very heavy. Our final design, we have a cutout of our wing airflow here. This reduces the weight of the wing as well. And it's also very important to notice here on the leading edge, the insert of the 1/32nd sheet of balsa. This facilitated our engineering, our manufacturing time. And also, if you could just wonder, if you didn't have that cutout, you'll have to just pretty much cover the entire sheet of balsa, of the wing with balsa with 1/32nd. That would increase the weight of the aircraft drastically. Next. So for the fuselage, we have 3 different iterations, and I'm just going to touch up on the final iteration from last year's presentation with ABAB. We took into consideration their recommendation to add a vertical and horizontal stabilizer. So here we have a modular fuselage. This modularity allows us to pretty much include our configuration for a flying wing and also a conventional design. Here on the 2 front bulkheads, you have 2 holes where we have the configuration for the wing, the flying wing. And in the midsection on top, we have a configuration for the conventional design as well. Next slide, please. So our tail attachment is pretty much attaching the fuselage and the tail to the vertical surfaces of our tail. And this attachment was a little heavy on the side, made our aircraft a little tail heavy. So we decided to pretty much increase the length of the attachment and pretty much have the horns taken out at each end maximum. This reduced the material of the dorsal tank, that making our aircraft less heavier and making our coming back our moments. So for the manufacturing, in any engineering application, you always want to consider manufacturing, and pretty much this is a basic layout that we send to our laser cutter. We try to integrate all our components into one sheet. This facilitates the laser cutting time, meaning we're saving money and we're also saving time for the guys to set up the files. Next slide, please. So for the wing assembly, thanks to ESO and the Aerospace Engineering Club, they've graciously provided us with their facility so we can assemble our plane. here we have the top wing layout. We have here just the skeleton of the wing. You see the two carbon fiber rods going through. And the control surfaces were attached using CH hinges. This is a typical application for RC aircraft. And as you can see here, just the final prototype of a wing. For the fuselage assembly, we try to make it as easy as possible so anyone can assemble it. We have just a total of 6 components assembling the fuselage. And this makes it very easy just in case during competition we do crash land and it fails. We can easily assemble another fuselage on the spot. Slightly. So within any engineering system, you have subsystems, right? So for our case, we have the wing, the fuselage, and the tail. And each of these subsystems also includes subsystems that have motor, battery, and all these components integrated. So we have to be very careful on how we integrate these components, and also considering that we have a 6-inch diameter container that needs to be coming out and easily assembled within 5 minutes. Next slide, please. So here's our prototype. This is the ISO and top view of our prototype.
Throughout the entire project, we kept a detailed spreadsheet of all the things we bought, because we're encouraging our fellow students to rebuild our plane. More importantly, here to point out is the battery. We use an 850 milliamp hour battery, lithium-ion, 6x4 propeller, and we use a Hacker 820. We also bought some 7x5 propellers to make to see the difference between the thrust. And to get a general idea how much we spent on this project, it was around $960. So this included the laser cutting services and all the intricate electronics on the plane. This also included the services for the flying wing. So there is the laser files are set up and are meant to be sent out to the manufacturer to cut out the plane. And that configuration is also included in this budget. So technically both configurations were around $960. The total man hours we spent on this project was around 800 hours. The majority of it came from the research and development. A lot of these things we had to get out and learn on ourselves, like aerodynamics and aerostructures. Same thing with software. We had to learn a lot of the CFD software for ourselves. So that added up. And to get a rough idea how much a project like this would cost in the industry, generally speaking, an entry-level engineer is paid $31 an hour. If you do the calculations, this project in the industry would have cost around $26,000. Again, this is more so because of the research and development. So this gives perspective on how things work. Now, before flying the plane, we conducted a risk assessment. Due to the sake of brevity, I have to, we only included the top 3 risks. These are the loss of power to the motor, a loss of control surface, and the loss of the receiver. So to mitigate those types of risks that can involve either property damage or human damage, we will be checking the battery post and pre-flight every single time. We will be also visually checking to make sure there's no risk in the ultrascope. And the receiver has a fail-safe, meaning it's out of range, the control system shuts off. And finally, we're also instructing our pilot to lose the aircraft if anything goes wrong. We're not interested in recovering the aircraft if something goes wrong. So this is a video of the test flight. This was up at Marcos Park. The headwind that day was about 20 miles per hour, so it made launching the headcraft very easy. You might notice that the actual video is not stabilized; it's kind of wobbly. That's because, for the sake of this video, we strapped a GoPro, which is 2 inches by 2 inches, on the top of the aircraft. Now, this is equivalent to attaching a flat plate. So a lot of the flow after the GoPro became turbulent, so the control surfaces were pretty much, for the lack of a better term, useless. But our pilot, Keyshawn, he mentioned that he never felt like he lost the control at all. For the sake of time, I'll skip till the landing. And so this is the hard landing. We did lose a propeller due to this landing. We have a propeller around here. But the propeller are easily interchangeable and they are pretty cheap to come by. And there's also different types of propellers in the future that we can incorporate that close up when the flow stops. So the result. So we had originally designed this airplane to be around 1 pound. The actual weight is 1.2 pounds. The payload weight, we ended up using copper plates. In our first initial design, we wanted to use tungsten plates, because tungsten is a very dense product. But tungsten is also incredibly expensive and very hard to machine. Still though, the payload weight was around 3.6. Because of this, we achieved a payload fraction of 4, which is our target payload fraction. Payload fraction is the empty weight of the aircraft compared to the total takeoff weight of the aircraft. So this means for every for every pound of aircraft weight, there was 4 pounds worth of payload weight. The wing loading was around 32 ounces per feet squared, which is competitive. And the assembly time was around 5 minutes. And as you can see, the entire system can fit inside that too, and it's roughly the weight. Now, competition is this weekend, so we don't have the results for that competition. However, we are expected to pass the technical inspection, and we are expected to finish in the top 5 schools. This is a quick rundown of the point system they have in the competition. Our content is 35 inches long, so we're expected to get between 40 and 60 points. However, there's multiple circuits, so these points stack up. So we're expected to hopefully reach in the top 5 schools if nothing goes wrong with the system. So our conclusion: the objective of this project was achieved. We deployed and successfully launched a United class aircraft with a payload fraction of 4. More importantly, we also learned a lot about project management and logistics planning. This project made us get out of our comfort zone and call manufacturers and producers and get in contact with people in the industry and develop that type of professional relationship with them. As well, we think we improved our CAD modeling skills and our parametric design skills. A lot of these variables in airplane designs are reiterative, so they feed into each other. So you have to continue to do them over and over again. And we also feel through this project we engaged in a practical engineering scenario. So for our future work, we were really ambitious in the beginning of this project. We threw out a lot of ideas for the wing assembly. We would like to revisit those ideas, maybe some sort of spring-loaded mechanism or some block-by-block wing. There's also the inflatable wing we thought about. We would like to revisit those wings to see if we can further reduce the container size. We also want to maybe decrease the assembly time. We can decrease the assembly time by getting more used to the system, getting more confident with putting the pieces together. Right now we're looking at assembly time of 4 minutes. We also would like to introduce an aerodynamic fuselage to see the performance benefits. And more importantly, we want to continue fostering the interest in aerospace studies here at FIU through this project. We are leaving this semester, so we're hoping to leave this project behind and see how our students can improve them for next year, and hopefully outdo us. These are the few things we do with the FIU Aero Club. I mean, a big thanks to them. Without this project and their support, these projects would have been impossible. This is our Gantt chart. We kept to Gantt chart. We kept our project management time to the bone. We did not stray. And these are our related standards. More important here, we have the FAA. The FAA requires us to register our UAV if it weighs over 5 pounds. Right now it's only weighing 4.8 pounds, but just to be sure, we still register it for them. And global learning. At this competition, we have schools from all over the world, so we're kind of interested in meeting up with them and seeing how they design their airplanes and what was their design ethics. Because how we design here in the United States might be different how people design in South America or Europe. And we would like to thank our faculty advisor and our project advisor, Igor Sukunov, and Professor Tosunoglu. Professor Sukunov is not here with us. He's not here with us right now, but he did help us a lot, and Tosunoglu helped us a lot too. And also our sponsors who donated the money for us, and of course FIU Aero East Competition. I'd like to open the floor for discussion.
So I'm glad you went with this design now with the wing fuselage. Something that I would like to know is, did you consider dihedral in your design? If you did, why didn't you choose to have a wing with some angle in it rather than a straight line?
Okay, so the flying wing had a dihedral built in originally. This one, we didn't want to do it because of the way we were going to connect the wing. Initially, you saw we just assembled it using rods and tubes. By accident, I will admit, because the deflection of the wing is relatively high, it gives it an effective dihedral line. So we just stuck with it at that point.
Did you, now that you mentioned that, did you do any analysis to confirm that if this flies during inclement weather, the wings are not going to collapse? Since they're already preloaded?
Yes. We test fly. We did a test flight flight in very bad weather for this size of aircraft. It performed fine. It had some issues with stability, as we mentioned earlier. However, all the analysis that we did was without the ultracoat. The ultracoat adds a lot of rigidity to the wing because it's basically a giant tension element on the whole surface. So we felt that if it was safe, using the very safe assumptions that we made for the material properties, it was going to be safe with the other extra layer of the ultracoat.
And last observation, you showed the video with the GoPro. Did you fly it without it? And did you have a trimmed flight, or you had to constantly do corrections to your flight?
I was personally not the pilot, so
So actually, our pilot is here. If you could ask him if he's ready.
I noticed that the camera was set in the front of the aircraft.
So you flew it without the camera though?
No, we didn't fly without the camera. We are planning on doing that later today though. But when the camera was placed in front of the aircraft, like it was right behind the motor, it shifted the CG forward. So I did notice I had to give a lot of up elevator to keep the nose up. So I do expect it to fly level without the GoPro in front of the CG.
Do you have a plan to include counterweights in case that you have a tail heavier, your CG is aft of your wings?
Well, the way that the fuselage was designed in the two bulkheads that they originally introduced is you can move the actual payload bay fore or aft depending where your CG is. Again, this is also to introduce a flying wing design because we still haven't given up on the flying wing. We have slots for the flying wing there, and that needs a different CG. So the actual payload layer, which is that copper bracket, that copper rectangle there, can be moved inside the fuselage or aft depending where you want to set it up. So in a sense, the counterbalance is already built in. It's just all in, and all we got to do is just wedge it one way or wedge it the other.
I would look into that today. We tested go in with a trimmed aircraft before you add the weight. You don't want to have that situation where you launch it and then your aircraft just stalls and you lose your all your time in this project. So today made the adjustments to make sure that you can achieve a trimmed flight with minimal impact from your pilot.
So the controls have a trim set, so you could
Yes,
adjust
they
it.
do.
So, and then you trimmed it on that one because did you
I
do a
didn't trim it.
barrel roll
I
on
did
that?
not. No.
Did you?
With payload, doing a barrel roll is not a good.
No, I mean I thought I saw it on the video.
Oh no. But we
It
did
looks like
not.
it
We
was-
did
was
not
it-
trim it the last flight.
It was a save.
So why did you design it to belly land? When you know perfectly well you're going to blow up a prop every time you go in.
To design a landing gear, to design a proper landing gear, you're looking at something, a structure that takes at least 3-4 times the load of the plane. So we're looking now at a structure that needs to take about 50 pounds of load of dynamic load, none of a static load. So now we have to design something that's DP or something that's made out of metal. This competition, the sole purpose of this competition was to decrease the weight of the aircraft, the empty weight of the aircraft, while increasing the payload, the capacity to carry weight. So by introducing a landing gear, it was too much an offset. So now we have something because this landing gear is not going to be tracking to the belly. This landing gear will stay out forever. Now we're introducing a structure that deflects flow, that can create more drag and increases weight in the aircraft. We felt through cost analysis that losing a propeller potentially every single time is a lot better for this competition than introducing a landing gear. The propellers are not that expensive. They're made out of APC. 10 cents.
Did you do an analysis to verify that you always break the propeller, not break the engine?
Oh well, we haven't done. We didn't do that analysis, but we do have a redundant engine. We did buy spare parts just in case. Like I said though. A system like this does, you do need to use it a lot to find the quirks of it. You know, something that we did not, and this is probably for all engineering projects to do. Something that you design for, something that you can do a risk assessment for, will never show up until you continuously use your product. It's all a battle of statistics. So maybe something happens that we did not plan on for, but until it gets there, we won't know.
Okay, and the last question I have is, when you actually showed us the video, was the payload in place?
Yes, yes, payload.
So the payload was in place, okay. And where's competition?
Lakeland.
Lakeland, you're heading up there?
Yeah, they're heading.
Okay, great.
So just a couple of your observations for the next team that does this. Look into ducted fans. That will reduce your braking and prop every single time, or even placing the engine on top of your wing. And there was something else. Yeah, you could have damage to your shaft, your motor shaft. So again, just make sure you know that your risk assessment for your report.
Thank you. Yes.
Just, is there a dimensional limitation for the payload?
Yes, there is a limitation for the payload. For the cover. So initially, how we started this project, that was our payload bay. They gave us a 1.5 by 1.5 by 5 inches, right? So we had to find out a way how to carry that. Originally, first we went online. We saw different types of materials. We chose the density of tungsten. We chose the density of copper, and that's how we got a payload weight. And yes, so the initial design process began with the dimensions of the payload. But like you saw in the video, we can equip something else onto the plane. It doesn't necessarily, for generator use, it doesn't necessarily have to be that. It can be something around the same size, but with the same weight.
And to build on that, the battery that we're using is very low power. So if you replace that with a 3-cell 2200 milliamp hour battery, our actual flight time right now is only like 3 minutes at full throttle. If we put a battery that size, you can have a loader time of about 30 minutes, no problem.
Do you have some altitude dimensions, like how high?
Well, that would be restricted to the receiver. I'm not too familiar with the receiver system, but
Requirements.
for the requirements at the competition.
We have to go above 100 feet.
Is there?
We have to launch it as a plane.
100 feet around that area.
Bang.
I'm sure they made a no-fly zone over the whole Lakeland, Florida that day. Hopefully, but we don't know the ceiling of that. But the receiver will probably kick in before it goes above 300, 400 feet. The Bell City.
I think there are no altitude requirements, just to have a
Yeah, it does. Yeah, the requirement is to fly around on a circuit.